I'm not going to do it. I was told when we went on that I should spit the water straight for the camera, but I won't do that. So, okay, let's go ahead and continue on the path that we're on, which is talking about random processes. We ended up last time talking about a very important class of random processes called Poisson processes. We're going to talk about another important class, and it's important because the way it rears its application in the area of both finance and physics, and that's the so-called Wiener process. The way that we do the Wiener process and the way that we visualize the Wiener process is as follows. We assume that we have a random walk of statistically independent IID random variables which are uniform. So we assume a bipolar Bernoulli sum process but we do it with a bilateral height. In other words, we flip a coin, and if it's heads, we go one step to the right. If it's tails, we go one step to the left. So it's bipolar. It's +1, -1, as opposed to 1, 0. And the degree of the step that we take is h, and the time interval that we flip the coin in is del. So we flip the coin every del seconds, and we take a step to the right or the left corresponding to h. Well, clearly the expected value of x of t is 0, since at any one time the chances are you've moved to the right is exactly the same amount as you move to the left by the same amount. The variance is exactly the same as a variance of a bilateral Bernoulli process. For a regular Bernoulli process, 0, 1, if you remember, the variance was NPQ. But in this case, it would be NPQ times the height. For the bilateral, it's not NPQ. It's 4 NPQ times h squared. The h squared, of course, is the degree of the step. So if we do a 50-50 coin flip, n and p are equal to 1/4, and this just becomes n times h squared. So this is the variance of the stochastic process. So these are the second-order statistics. Now, that's the Bernoulli process. Again, this is the repeated Bernoulli process, which becomes a binomial random variable. We are going to now take the limit as h goes to 0 and del goes to 0. So in other words, we're going to let these times between when we take the step shrink very, very small. And if we do that, we better make the step size very, very small also, because if we shrink the 1 to 0 without shrinking the other to 0, we get into all sorts of problems. So we take the limit as h goes to 0 and del goes to 0. So I think we better shut the door. We have a mob coming down here. We don't want them to enter in here and disrupt our lecture. Now, when we do this, it's much like the Poisson theorem coming from the binomial. We're going to have both of those go to 0 in such a way as to keep their ratio h squared over del a constant. So both are going to go to 0, but we're going to keep alpha, which is the ratio of h squared to del, a constant. Under this condition, the variance of x of t becomes alpha times t squared. If t, by the way, t we've replaced by n del, because by taking this limit as del becomes very, very small, we're going into continuous time. So the variance of xt becomes alpha t squared. So we have a process whose standard deviation increases linearly with respect to time. By the central limit theorem, x of t is immediately Gaussian with 0 mean and this variance. Why is it immediately Gaussian? Because in any finite time interval, how many steps have we taken already? We've taken an infinite number of Bernoulli steps, right? Going one way or the other, and so boom, we're at the central limit theorem immediately. So this is a Gaussian process, even though we started with this bipolar moving to the right and left. So, and this is indeed what the Wiener process is. It is a stochastic process which is Gaussian. It has 0 mean, and it has a variance of x of t equal to alpha t squared. What's the I? Variance of t squared. I don't know what the I is. I didn't belong there. Now, the interesting thing is we could use any 0 mean process to generate the Wiener process. you'll notice two things. Number one, I'm very inconsistent in the way I spell wiener. I spell it this way here and this way here. I noticed that. So that's one thing you should notice. The second thing you'll notice that the Wiener process is a result of application of the central limit theorem, which is applicable to just about any, not any, but just about any of the different stochastic random variables that exist. So we could have used, for example, an exponential random variable as opposed to a Bernoulli trial. Or we could have started out with a Gaussian step, wherein you took relative grades of steps to either side. So we just find it useful to use the Bernoulli because it's the most simple of the random variables to deal with. So this is the Wiener process. Here are some examples of Wiener processes. This is for alpha is equal to 1. It's a very simple matter to go to MATLAB, generate a random Gaussian vector, rand n, and then do a cumulative sum operation on it, and boom, if you shrink down the time domain sufficiently so that it looks continuous, you get a Wiener process. And this indeed is a Wiener process. It always starts out at 0, and you'll notice that as time increases, that the standard deviation or the uncertainty of where you're going to be at increases also. In fact, what we have shown is that this uncertainty increases linearly with the slope of alpha, alpha being a parameter of the Wiener process. And right here at the origin, everything starts out at 0. The Wiener process is used in Brownian motion, where you have a small particle being bombarded randomly by water molecules, and it's moving around in a stochastic manner, the classic random walk. Another place that it is used quite extensively is in the area of finance. Boy, I'm totally inconsistent in Wiener. I see it's Wiener here and Wiener here. What's right? It's W-I-E-N, right? Okay. I-E? Okay. And it's, who's German? It's what?
It's EI.
It's EI? We have an EI, I-E?
It's IE.
Okay. It's in the book. What is it in the book? Look in the, let's get the definitive ruling on Wiener. It's IE. And if you're German, you would pronounce it, oh, would you? Would you?
The else go walking, the second one does talking, so W-I-E.
So it's still Wiener.
Right.
Okay, so it's not, okay. Very good. So it's not Wagner, it's Wagner.
No. Mine's spelled V-I, and it's, you say I.
So you say it's what?
Wiener.
Wiener, okay. Okay. Aren't you glad we're not in an English class? I wouldn't know how to grade you. Okay, here's the way it works in finance. I'm going to outline it without going into a lot of detail, but I am going to show you the formula that is used the most in financial engineering. In fact, the formula that I'm showing you is the foundation for most of the financial engineering. For example, in the pricing of securities, the pricing of options, pricing of futures. There's a great book by Hull, H-U-L-L, and it has the word derivatives in the title. And he goes through all of the continuous time economic models, and the formula I'm showing you is the foundation for all of those models. It's the underlying assumption of this analytic area in financial engineering. Of course, there's other things which go on, but the introductory material is all based on this concept because the math flows out very easily from it. So here is the Wiener process in finance. S is the price of a security. A security is a fancy word like for a stock or a bond or something like that you buy. And we have mu as an inflationary force, and we won't get into that, but you know that if you have an inflationary force and you go to a savings account where there's no risk, you know exactly how much money you're going to have in the savings account in a year, right? If you go in and you put your money in at 10%. And what happens if you compound it in continuous time? A small change in the amount of money that you have in your savings account is proportional to the amount that you have in your savings account, right? So if you have more in your savings account, you're going to get a bigger percent. So whatever is in your savings account whatever is, there's a proportionality constant here, so the amount of money that's added in terms of interest is proportional to the amount that you have in the savings account, right? And this would be over a small period of time. This mu is your interest. This is a simple differential equation, which of course has a solution. S is equal to S naught times e to the mu t, which is the exponential growth in your savings account, especially if mu is a really, really big number, right? So it is one of those situations. Now, this is totally with the lack of any sort of uncertainty in the model. Now, with uncertainty in the model, such as stocks and bonds, there is something which they call a volatility. Now, the volatility is nothing more than the standard deviation. It's nothing more than the standard deviation of the stochastic process which is driving the market. So we look at an actual price tick waveform, and if it just wiggles a little bit, you know, like some of the established stocks, then we say that it has very small volatility. If, as a function of time, it goes all around like the dot-coms did, then we say it has a high volatility, and clearly that has a high standard deviation. That's a stochastic process with a high standard deviation. Now, if you have a high volatility, the amount of money that you make or lose is proportional to the volatility, right? If you have a big volatility, the chances that you make a lot of money are, or lose a lot of money is proportional to that. So in that case, the small amount, the amount of change you have in your portfolio does have this term, mu s dt. This is the inflationary force. Plus, it has another term which gives a proportionality constant of the standard deviation. If it wiggles a lot, you have a chance of great gain or loss. And this is also proportional to the amount of money that your stock is worth, right? If you have a big swing in the market and you own 10 cents, well, your change isn't going to be as much as if you own $1,000 worth. So it's proportional to what you have in the stock. And this is times dW, where dW, let me make sure that I'm using this as, okay, no, dV is what I use in my notes, so let me use that same thing. dV of t, where V of t is actually a Wiener process. What did we decide? IE? Yeah. Okay. So V of t is a Wiener process. And this is the actual differential equation that is used by people in financial engineering to derive many of the pricing strategies they had. A few years ago, I'm trying to think of the names. The name of the formula was Black-Scholes, and then there was another guy named Jack Merton who actually used this to do pricing options. And they were able to use, starting with this formula, derive options pricing, and it won them the Nobel Prize in finance just for a mathematical derivation. And it's one of the models that is used today. So it's a very familiar foundational sort of equation. Now let's look, if V of t is a Wiener process, and say it's a Wiener process which is by a Bernoulli trial, what is dV? That's a small increment in a Wiener process, right? But what's a small Wiener process increment? It's either a step to the left or a step to the right, right? That's what a small dV is. In the absence of this inflationary force here, what this is basically saying is the amount that you make is proportional to your step size, sigma here. And by the way, S is, of course, a function of t. I didn't put that in there explicitly. It's a step size, and the best you can do is you look at the volatility of your stock, and tomorrow, with an equal chance, it could be on either side with a step. I shouldn't say tomorrow. I should say in an incrementally small dt version. So in other words, the stock market is, by the financial people, totally modeled as a random walk. And there's no way that you can forecast it. Now, finance is a soft science. Once you have a model, there's no way you can verify it like we can in engineering. And so there's a lot of dispute. It's simply a model. There are people called chartists, which say that you can look at the way that the stock is moving, and just by looking at the chart, you can forecast the future and things like that. The people in classical finance are typically not believers in that. That the best thing you can do in forecasting the price of a stock tomorrow without looking at any other thing is to say it's the same price as today, plus a little inflationary force. Okay, so that's the result for the Wiener process. Very interesting. I haven't taught 508 for a while, but when I did, we actually went through the derivation of the Black-Scholes equation. And it's something, that's a great thing about being in engineering, especially electrical engineering. If you're not an electrical engineer, I don't mean to hurt your feelings. But we learn such a broad scope of different topics that we can be dangerous in just about any field. We really can. It's delightful. Okay, let's get back to the idea of stationarity, or I'm sorry, stochastic processes. I'm going to introduce now the concept of stationarity. Let me first of all heuristically explain to you what stationarity means. A stochastic process is stationary if its character doesn't change with respect to time. Its character doesn't change with respect to time. In other words, if you looked at the stochastic process today, it would kind of look the same as it did yesterday, and it would look the same as it did tomorrow. So it's kind of has the flavor of time invariance, but it refers to actually the character of the underlying stochastic process. White noise, for example, if you went shh, it sounds the same all the way through that process. That would be something we would say, at least intuitively, would be stationary. My lecture to you is not stationary because the character of my voice signal is different with respect to time. Now I'm talking to you, so things are wiggling in the air, all these pressure things, and then there's quiet, and that quiet is different from when I'm talking. So that's not a stationary process. The statistics themselves are changing with respect to time. So this is what we mean by stationarity. Now, stationarity has some specific definitions, but the concept of stationarity is as I have described it. It's much like the case of central tendency to a probability density function. It's where it's centered, right? So you can use the mean, the mode, or the median in order to characterize that. There's different ways to look at central tendency. In the same way, there's different ways to talk about stationarity. And we'll talk about some of those general ways. But the general concept has a general definition, much like I talked about it. The character of the stochastic process is not changing with respect to time. How come I started in the middle of the lecture here? I don't know. Okay, so a stationary random process is means that the stochastic process does not change character with respect to time. I gave you some examples, the idea of white noise being a stationary process, speech being a non-stationary process. However, people that do speech, and I'm not an expert in speech, you'd have to talk to Professor Atlas or Professor Ostendorf to know more about this, but my understanding is that in speech there are certain portions of speech which can be modeled as stationary. For example, the vowels. See, if you take a vowel, vowels are the only thing you can sing because you can keep them going. You can't sing a B, right? You can't go. You can't hold a B, but you can hold an E and an I. E, I. Okay, so you can hold those, and those you can see might be a stationary process. I would say E. That would be a stationary stochastic process. My son, by the way, is studying to be an opera singer. So I'm learning a lot about the human voice and proper training and how to do vowels. Okay, so and if I clap, for example, that's noise, right? It's not a stationary process. In fact, it's a very impulsive process. So that would definitely not fall within our concept of stationarity. There are different types of stationarity, just like there's different methods of central tendency, mean, mode, and median. We have different types of stationarity. We'll have what we call the strict stationarity. And strict stationarity, we really hold up the stochastic process to a lot of different tests. You got to be really special if you're stationary in the strict sense. Then there's stationary in the wide sense. Well, in the wide sense, we're going to let the stochastic process in our club and not be too picky about who we choose. So it's a much more sloppy or a wide sense sort of stationarity. So stationary in the wide sense is also referred to as wide sense stationary. And then there's a type of process which is cyclostationary. And this is stationary in a periodic sense. There are certain waveforms that are repetitive and they're different every period, but they kind of look the same every period. If you looked at somebody's heartbeat, for example, wouldn't that be loop, loop, loop? Each of the periods kind of look the same, but if you looked at them in detail, they would be different. If you look, for example, at over a short period of time, the temperature cycle during the day, temperature cycle would go up and then down at night, and up and down at night. And it would be repetitive, and it would be different in its details, but it would have a cyclic sort of similarity. This is the concept of cyclostationarity, and we'll visit that also. So let's then talk about strict stationarity. X of t is stationary in the strict sense if for all k and tau and choices of t. Wow, this is a lot. Okay, is that clear? Let me tell you what that means. Let's go to the board. Do I? No, I guess I don't. Okay, I thought I gave an example there, but I don't. Here's the idea of strict stationarity. I take a value of x of t, and I choose a value of k. K corresponds to the number of points I choose. So I'm going to choose a point here, and a point here, and a point here, and a point here. So I'm going to use k is equal to 4. Now, I could use any value of k I want to. If I do that, I'm going to get different random variables corresponding to this point, and I'm going to get a two-dimensional random variable, right? No, I'm not. I'm going to get a four-dimensional random variable. And say this is the density function for those choices of random variables, for those choices of four random variables. Clearly, if I change the locations here, I'm going to change this function, right? Now, stationarity means, again, what does it mean? The character doesn't change with respect to time. So that means if it doesn't change with respect to time, if it's the same before, now, and in the future, then that means we should be able to move this over, say, an amount tau, take a new point here, move this over tau, take a point here, move this over tau, take a point here, move this over tau, take a point here, and we're going to have some new random variables. Each one of these intervals is exactly the same shift tau. Now, if the random process hasn't changed with respect to time, the four-dimensional probability density function describing the red points is going to be the same as the four-dimensional density function describing the black points, if the character is not changing with respect to time. So the new points are f sub x of, let me be explicit here. Unfortunately, being explicit also means being obtuse. Okay, so that's the result here. Now, when we move this over, this is going to be x of t1 plus tau, x comma x of t2 plus tau, x of t3 plus tau, x of t4 plus tau. That's just the subscript. And the argument, excuse me, I'm doing the argument on the next line, would be x1, x2, x3, x4. It's still just a function of 4 variables. But now the variables are t1 plus tau, t2 plus tau, t3 plus tau, and t4 plus tau. Next time I'll use only 3. So that's the density function for these new 4 points, which I obtained by taking the old 4 points and shifting them all over by a factor of tau. If we have a stationary process, this density function should be the same as this density function, if it's stationary. And this, if this is true, then we say that this process is stationary in the strict sense. Not only does this have to be true, but it has to be true for all k and choices of times. In other words, I would have to do this for 87 different points. I would have to look at all combinations of 87 different points and make sure that those 87 different points, when I shifted them, had the same density function as before I shifted them. That's a pretty drastic, pretty strict definition for stationarity, right? And so you can see why this is referred to as being stationary in the strict sense. Is strict spelled correctly? Okay, good.
Is it necessary to have this as a multi-time function? I mean, is it just as equivalent to say that your CDF at time t1 has to equal the CDF at time any other time t1 plus tau?
No. No. The question is, if this was only true for the first order,
Right.
wouldn't that be sufficient to assure all of these others? No. The reason is, and think with me if you will, remember that if you have, for example, a second order that's jointed, you can get the marginals. And you remember the marginals don't dictate the joint. Right? So the second order has more information than the first order. The first orders are just the marginals. So the second order actually has the structure of the interrelationship between the two random variables, which the first order doesn't. Now, the interesting thing is that if this is stationary in the strict sense for, say, k is equal to 4, it's also stationary in the strict sense for k is equal to 3, 2, and 1. Because from these higher density functions, you can generate the lower dimensional marginals. So you can go from big to little. You can't go from a lot of points to a few points, but you can't go the other way. You can't go from a few points to a lot of points. Okay? Except there's one case where you can, and we'll visit that later. But what do you think it is? There's one case where if it's stationary, second order, that is, if this happens just for the second order, x1 and x2, then it's stationary in the strict sense. It does go up. There's one exception, and it's when it's a Gaussian random process. That's right. But in general, it's not true. In general, it's not true. It does turn out that it is true with the Gaussian, which is one of the reasons that we really like the Gaussian. It's one of the reasons that people in finance deal with Wiener processes, because it's Gaussian, and you can do a lot of stuff with Gaussian analytically. Okay? So this is the definition of strict stationarity. X of t is stationary in the strict sense if for all k and tau, the choices of, for a k, you choose k points, and the density function for those k points is exactly the same as for those k points shifted. In other words, all of the cumulative distribution functions are independent of the choice of the time origin. You'll notice that shifting is kind of a relative thing. You can either think of shifting the function or you can think of shifting the time origin. They're relative to each other. So that's the definition of strict stationarity. There are some, oh, and by the way, I should mention that there's the equivalent definition for discrete time random variables also. All IID random processes are strictly stationary. That's interesting. An IID random process is one wherein all of the samples of the stochastic process are independent of all of the samples of the other stochastic process, be it in the discrete sense or the continuous sense. If we have a a continuous case, then if we have independent points, that is our density for independent points, if they are indeed independent, the joint can be expressed as the product of the marginals, right? The joint can be expressed as the product of the marginals. And this is also equal to the marginals shifted. Because if it's IID, these are going to be exactly the same as the density functions or the distribution functions corresponding to a shift, since every random variable sample has the same distribution. So an IID random process is stationary in the strict sense. The telegraph signal. Remember the telegraph signal, which you flipped off and on and off and on? Do you remember our definition of the telegraph signal? You studied for it in the last test, where you had a number of Poisson points, and you started this. Oh, no, I guess it went down to 0, didn't it? Did it go down to -1? Yeah, it went down to -1. Okay, this was the Poisson random variable. Now, you might say that this is not stationary, and it isn't stationary generally unless you do the coin flip. And from now on, when we refer to the telegraph signal, it'll be the coin flipped version of it. What do I mean by that? We do a telegraph signal as we defined it before, then we flip a coin. If it's heads, we keep it this way. If it's tails, we multiply it by -1 to flip it around the other way. Okay, so this is what I mean by that. You remember the coin flip or the flip theorem says if you do that, the expected value is always 0. That was the flip theorem. So we're always going to do the coin flip version of the telegraph signal from now on. If we do the coin flip version of the telegraph signal, then the telegraph signal is strict sense stationary when the origin is randomized. That's the flip theorem with a 50-50 coin flip. We can prove this using the independent increment property. Let's take a look at that if we can move over this way. Okay. This is the strict stationarity manifest through the probability mass function. The probability that this is true is equal to this chain of probabilities because of the incremental process, which in turn is equal to the same exact results with a corresponding shift associated with it. So the telegraph signal turns out, because of these equivalences, turns out to be, if we substitute the shift in here, we get exactly the same thing. So the telegraph signal also turns out to be, with the flip, strict sense stationary. These become hard to say. Strict sense stationary. Let's look at some of the required criteria for being stationary in the strict sense. We're going to look at necessary conditions. One of them, if x of t is stationary in the strict sense, the mean must be constant for all time. Certainly, if you have a stochastic process whose character does not change with respect to time, then its expected value needs to be a constant for all values of time. If the expected value were not a constant with respect to time, then where it changed, well, that would be different from where it was different, and so you would have a stationarity. So that's one of the criteria, is that the expected value of x of t is equal to m, where m is not a function of time. It's equal to a constant. Secondly, is the autocorrelation is only a function of the distance between the 2 points. Let me explain to you what I mean by that. We have an autocorrelation here, and this is going to be a value of, say, t and tau. And we are going to sample this autocorrelation, and we are going to obtain an x of t, and we are going to obtain an x of tau. And of course, we get the autocorrelation by taking the expected value of x of t times x of tau corresponding to these 2 points, right? That's the autocorrelation. What we're going to do now is exactly what we did with strictly stationary. We're going to go this over, let's say, by an interval of c this time. And we'll look at two more points. And these 2 points are going to be x of t plus c and x of tau plus c. And we're going to have now, if we get the autocorrelation here, we're going to have the expected value of x of t plus c and x of tau plus c. Now, if indeed this is a stationary process, this better be equal to this, because we've just shifted things, right? And if the character of the stochastic process is not changing with respect to time, then those two expected values should be the same. In fact, the density functions, if in a strict sense case, the density functions for these two random variables are exactly as the same as for these two. So clearly, if that's true, the lesser criteria that the expected values be equal follows immediately. This leads us to the following conclusion, that the random variable really doesn't matter where the 2 points are located. Rather, it is only dependent on how far the 2 points are separated. Doesn't matter where they're located. If I take these 2 points, the autocorrelation, the expected value of these 2 points, if I keep this interval the same between my 2 fingers, the expected value of these 2 points is the same as the expected value of these 2 points. It's the same as the expected value of these 2 points, the same as the expected value of these 2 points. So it doesn't matter where I put this interval along the time axis, the expected value is going to be exactly the same. Well, what is that interval? This interval is equal to t minus tau. That's the interval that I'm talking about. So if we have a process which is stationary in the strict sense, then the autocorrelation is only a function of the separation between the 2 points. Doesn't matter where those 2 points are, it's only a separation between the two. So we have two criteria that are special cases. We have, first of all, the expected value of x of t is equal to a constant. And the second one is that the autocorrelation is just a function of the difference between the two variables. So these are two necessary criterion if we have a process which is stationary in the strict sense. You will notice that these processes also define a kind of stationary, a more sloppy type of stationarity. And we'll refer to any stochastic process that obeys this as being stationary in the sloppy sense or in the wide sense, in the more general sense. So 1 and 2 correspond to a wide sense stationary stochastic process. Remember our definition for strict stationarity? Had to go through a lot of hoops to specify that. This is wide sense stationary. We only have to establish two things. The autocorrelation function is just a function of t minus tau, and that the expected value, the mean, is a constant, does not change with respect to time. So clearly in the set of all stochastic processes, we have strict sense stationarity here, and we have a wider case, wide sense stationarity, and clearly the strict sense stationarity is a subset of the wide sense stationarity, right? Okay, so this is an easier type of stationarity to establish. The random walk is not wide sense stationarity because the expected value increases with respect to time. Do you remember the expected value of the random walk was equal to, not the expected value, the expected value is 0. The standard deviation was proportional to t. The standard deviation was proportional to t. So clearly the variance changed with respect to time, which implies that this has to change with respect to time. So the random walk is not stationary. By the way, in this definition that we have for wide sense stationarity, instead of the autocorrelation, one can substitute here, instead of the autocorrelation, the autocovariance. So the autocovariance is just a function of t minus tau 2. You can actually combine these two and show that the autocovariance is indeed just a function of t minus tau. So x of t is wide sense stationary if the mean, the expected value of the mean is always equal to a constant, and the autocovariance is just a function of t minus tau. I think that's the same thing. Now let's look at some interesting things. Let's look at wide sense stationary stochastic processes. Something which becomes very, very important is the following recognition, that if we were to have a current, which was a stochastic process, going through a 1 ohm resistor, then the power would be equal to the square of the process. So in general, what we've already shown is the expected value of the power is equal to the expected value of the second moment of the stochastic process. In general, this is true, that the autocorrelation is equal to the expected value of x of t and x of tau, and that if we evaluate the autocorrelation at t and t, we've looked at this already, this is equal to the expected value of the x squared. So we've already established that the second moment of the stochastic process is also equal to the expected power. Notice what happens, however, if we have a wide sense stationary process. If we have a wide sense stationary process, what do we know about the expected value of x squared? We know that it is constant. And that if we have a wide sense stationary process, that the autocorrelation evaluated at the origin is equal to the expected value of x squared of t is equal to the expected value of x of t. Let me elaborate on this just a little bit. We know that this is true. This is the definition for our stochastic process. If it is wide sense stationary, then this is just a function of t minus tau, is what we decided. So it's only a function of the difference between t minus tau. So what's interesting is if we wanted to make this just a one-dimensional function, say r sub x of tau, well, how do we vision this? Here's our process. Here's some arbitrary value of t. Here's some arbitrary value of t plus tau. This is x of t. This is x of t plus tau. The autocorrelation between these 2 points has nothing to do with t, right? It just is dependent upon the separation between the two. So we can write this as equal to the expected value of x of t times x of t plus tau. So this is one way to write this. And as long as these two values are sampled such that the distance between them is tau, then that's r of tau. So you could do the same thing. You could do the expected value of x of t times x of t minus tau. Now, let's see. Well, let's do it this way. T minus tau and x of t. Don't you agree that these are also 2 points which are separated by an interval of tau? Right? Or you could write it as the expected value of x of t minus tau over 2, x of, some people like this formula because it's much more symmetric. But isn't the distance between these tau? That's all that we require in the expected value. So all of these are equivalent. You might ask, well, where did the t variable go? You got a t over here, but you don't get a t over here. Well, that t disappears because of the stationarity. It doesn't matter where we start measuring the autocorrelation. The only thing which is important is the interval between there. You'll notice that as a consequence of this, if we take r sub x at the origin for a wide sense stationary process, what do we get? Well, we substitute in here, tau is equal to 0, we get the expected value of x squared, right? Which is, if we have a wide sense stationary stochastic process, a constant. It's the second moment, but that's also equal to the power, the average power. So the autocorrelation of a wide sense stationary stochastic process evaluated at the origin gives us the second moment of the stochastic process, which is equal to the expected value of the power, which corresponds to the average power. This is what you feel when you stick your fingers in a light socket. You feel the second moment. You feel this power here. You don't feel the average of the voltage, do you, when you stick your finger in a socket? If you felt the average, what would you feel? Nothing, right? But you feel something. This is what you feel. This is the second moment of the stochastic process. So this is what we're trying to say here. Okay, tell you what, let's go ahead and take our break, meet back here when the big hand's on the 6, and we'll continue along these same lines. During our break, we talked a little bit about the final. I looked it up here on the web. This is from the UW web, and it looks like this is for the last day of instruction is Wednesday, December 12th. That blows me away. Boy, the quarter went quick. But haven't we had fun? Here we are. We have 10:30. I'm sure you can read that. This is 10:30. Meeting. These are the times we're supposed to meet. That's Tuesday, Thursday, right? That's us. And so if we meet at 10:30, Tuesday, Thursday, then this is our exam time. So if we could zoom in on that. Okay. 10:30 to 12:20 p.m. Friday, December 14th. Huh? So that's when our final examination is. Now, for Ed students, I don't know if the policies changed. It used to be that Ed students were required to come to campus for the final examinations. So we'll go ahead and use that policy. So if you're an Ed student, we'll see you here on Friday, December 14th, 2001. My assumption is that that hasn't been changed. If it has, let me know and I will announce it. But right now, it must be that you do come here. What is that?
PM, did I read that right? 12:30 PM.
Oh, God. No, that is right. 10:30 because 12. When is 12 p.m.? Noon. So 12:20. Don't. Yes, it starts at 10:30 a.m. and ends at 12:20. Okay, so that's good. Okay, so we have that checked out on the web. Let us return to our lecture. Okay, here's a power example. When you stick your fingers in the socket, you know that you're going to get a sinusoid, right? What don't you know about that sinusoid? You don't know the phase, do you? Do you know the phase? No, you don't know the phase. We're assuming that we have good quality power generation. So let's assume that we stick our fingers in the socket, and what we observe is a stochastic process. X of t is equal to a times the cosine of omega t plus some phase that we don't know. Suppose that a is something which is known. What is a? 110 volts? There's 120? They changed it. Huh? Okay, no, that's 120. Okay, it depends what country you're in. So that's 120 volts. So A is fixed, but theta is stochastic. What's the value of theta? It's a random variable. What's a good model for it? Probably uniformly distributed over a period, right? Don't you think? That'd be a good model for it. So if we do the expected value of x of t, we've done this before, we get 0. So we integrate this over the density function for theta. And it turns out we integrate a cosine over a single period and we get 0. If, on the other hand, we look at the autocorrelation, this is something that we have looked at in the past also. We find that the autocorrelation is equal to x squared over 2 times the cosine of omega t minus tau. Do you remember us deriving that? If not, I can go ahead and derive it. But we actually did, we squared this and then we expand the cosine out in a trig formula. Part of the trig formula survived, the other part got integrated out to 0, and this was what was left. We've done this We have done this before. If you'd like me to redo it, I'd be happy to, though. Now, you notice something about this autocorrelation that we generated before. We didn't talk about it then, but now we see, the autocorrelation is only a function of t minus tau, isn't it? Every place there's a t, there's a minus tau. So the autocorrelation function is just a function of t minus tau. This is a wide-sense stationary stochastic process. If you see the autocorrelation, and everywhere there's a t, there's a minus tau associated with it, and everywhere there's a tau in front of it, there's a t minus. If they always occur like this, then this is just a function of t minus tau, and by definition, this is a wide-sense stationary stochastic process. The expected value of 0, this becomes the autocorrelation. So that means that x of t is wide-sense stationary, and it's wide-sense stationary, and it has an autocorrelation. If we take this t minus tau and we substitute tau into it, we get this thing which goes off the screen. This is an omega tau over here to the right. Well, and then here we go. What's the expected value? What do you feel when you stick your hands in the socket? You feel the Rx of 0, the autocorrelation at the origin, which we said was the expected value of the power, right? That's the second moment of the stochastic process, equal to the average power, and that's equal to a squared over 2. This cosine goes to 1. So that means the RMS voltage is equal to a over root 2. Have you seen that before? Yeah, that's in very elementary electrical engineering. When you look at a sinusoid and you ask for the RMS value of a sinusoid, you get the amplitude over root 2. You remember that? Okay, same exact result, except now we've derived it through this random variable sort of stochastic process way of doing things. So this is the amplitude you'd feel, and that's what would knock you on your feet, the a squared over 2. Let's look at some of the autocorrelation properties for wide-sense stationary stochastic processes. We've already seen that the Rx of 0 is equal to the expected value of the second moment. That's one property. The other one is that the autocorrelation is even. It's an even function. Not every function in the world can be an autocorrelation function. We first of all notice the autocorrelation function must be positive at the origin, right? Because the second moment's always positive. Second moment's always positive, right? So it must always be positive at the origin. It must always be an even function. Let's show that. It's actually really easy to do. If we look at r sub x of t minus tau, we get this. Well, that's exactly the same as if we switch around t and tau. Because x of t, x of tau are commutative, and we can flip them around, that means that it's also a tau minus t. So therefore, it is an even function, and we establish that almost in a trivial sort of derivation. So that's one of the properties. Quod erat demonstratum, QED. Another interesting problem is that the value at the origin, which we know is the average power, is always a maximum. Now, which means that r sub x of tau must be less than or equal to the value at the origin. Recall, and here's the proof. The proof comes back from, remember the autocorrelation? We said the magnitude was always less than or equal to 1. Well, if we look at the definition of the autocorrelation at t and tau and t, we get this expression. We know that this is less than 1. And if we just manipulate this very easily, we find out that indeed the autocorrelation is a local minimum. So this means that when we have autocorrelations, that we can't have anything with an autocorrelation that looks like this because that's not even. We can't have anything with an autocorrelation that looks like that because even though that's even, the origin is negative, so that can't be an autocorrelation. We can't have an autocorrelation which looks like this because this value here is not the maximum. The maximum is exceeded elsewhere. We can have an autocorrelation, however, which looks like this. There's nothing that says a correlation can't go negative. So this can be an r sub x of tau with a value at the origin of the second moment. You'll notice that it's even. Its value at the origin is the second moment of the process, and that the origin is a maximum of the entire process. It is also possible to have an autocorrelation wherein this maximum is repeated. This is okay, because all we said that r sub x of tau is less than or equal to r sub x of 0. So there's really nothing in this inequality that says this maximum cannot be achieved at other places, and indeed it can. It is a theorem which we won't prove that if we do have any other place besides the origin where this maximum is achieved, then the autocorrelation is periodic. It's a theorem we won't prove. Again, let me state it. If we have this autocorrelation at the origin and it is replicated at any other place, then the underlying autocorrelation is periodic. It repeats forever. You'll notice, for example, if we go back, if we could go over this way a little bit, please. This was the autocorrelation for the sticking your finger in the socket problem. You'll notice the autocorrelation is at the origin equal to the expected moment, which is a squared over 2, right, when the cosine goes to 0. But you'll also notice that because the cosine is periodic, this a squared, this maximum of the origin, is replicated at every period of the cosine. So it occurs at periodic intervals. So here's an example of an autocorrelation where the value at the origin, number 1, is replicated elsewhere other than the origin, and number 2 is evidence of the theorem that if that happens, then the underlying autocorrelation is a periodic function. So forward we go. Okay, here's the proof of that. Quota runner. How do you say that? Anybody know how to say that? Anybody take Latin? My daughter's going to school. She has to learn Latin, and I don't know it. Quoterat demonstratium. Okay. Now, here's the other property that we talked about. If r sub x of tau is equal to rx of 0 for some tau, then r sub x is periodic function. This is the example that we just saw with the cosine. In fact, I didn't have to go backwards. I repeated it here, but I forgot it. Okay. So this is the concept then of wide-sense stationary stochastic product, random processes. Let's review. Strict sense, all the density functions have to be the same, independent of where you shift. That's strict sense stationarity. Wide-sense stationarity, piece of cake. The mean must be a constant. The autocorrelation is a function only of the distance between the 2 points where you examine. That's wide-sense stationary. Stationary in the wide sense, stationary in the sloppy sense is what we would say if we were using a slang. I mentioned the concept of cyclostationary stochastic processes, heartbeat, the temperature, cycling during the day. What are some other cyclostationary stochastic processes that you can think about? The moon, right? The amount of light from the moon, amount of light from the sun, whatever period of 24 hours. So for a given time interval, period t, the behavior of the process, each period has the same character. Remember we said for stationary that the process had the same character independent of the shift? Well, here we're saying it has the same period, but it isn't independent of the shift. The shift has to be in integer multiples of this period, and then it has the same character. We have cyclostationarity in the strict sense, which saying no matter where you go in one period, if you go to another period, it has to have exactly the same random variables. Ooh, not good. I did something bad. Okay. So therefore, if one were to have a strict sense stationary stochastic process, a wide sense stationary stochastic process, maybe that looked like this. See, I'm trying to get periodicity, but with variations in the period. Strict sense stationarity for cyclostationary stochastic processes says that if I have 3 points here, and these 3 points have a certain density function, that if I take those same 3 points on another period, say here, here, and here. See, I've tried to replicate those exact same points here on these intervals of t, that this will also have a density function of f sub x. These 3 points will. And if it's cyclostationary, these two are equal to each other. And it doesn't matter what periods we take these in. and it doesn't matter how many points we choose in any period. Those probability density functions are exactly the same. So we don't shift by an arbitrary value of tau, we shift by periods. Let me ask you this. Strict sense stationary stochastic processes and cyclostationary stochastic processes. One is a subset of the other. Which one do you think it is? Strict is a subset of cyclo. That's right. Much like if you look at the class of periodic functions and you're to ask yourself, if we just had a constant, is that a periodic function? Yeah, it is. What's a period? Anything you want it to be, right? But it's kind of a degenerate case of a periodic function, right? In that same way, a strict sense stationary process is kind of a degenerate case of a cyclostationary stochastic process, when we don't care what the period is. Certainly, if I gave you a strict sense stationary stochastic process, the density function here would be the same as the density function here. That would be true, right? It would be true. So the strict sense isn't a degenerate case, kind of a special case of the cyclostationarity. Here is an example of a cyclostationary stochastic process. Let's suppose that we looked at a sinusoid again, and now we're not letting our phase be the random variable, but the amplitude is equal to the random variable. Then the random process is stationary in the strict sense. In fact, the t, the period of this is 2 pi over omega, corresponding to the frequency here. And the stochastic process is wide sense stationary in the stochastic sense because the same random variable defines that process over every single period, right? I mean, if you give me a value of a in one period, it's exactly the same as in another period. So clearly, all of the random variables are going to be equal to each other. For a wide sense cyclostationary random process, two criteria are required. One is that the mean must be periodic function. Doesn't that make sense? If you have a periodic function like this and you took the expected value of it, wouldn't you expect it to be a nice periodic function? The expected value of the cyclostationary stochastic process, that is one criteria. The other criteria is that the autocovariance is independent of integer shifts of the integers, or equivalently the autocorrelation, which means that the autocorrelation between these 2 points is exactly the same as between these 2 points. Whoops, I'm on the mean. Between these 2 points is exactly the same as between these 2 points if the separation is exactly the same. Guess what they refer to this as? Not cyclostationary in the strict sense, but wide sense cyclostationary. In other words, it's a sloppy way of talking about cyclostationarity. Okay? And look at the time we have. Let's look at something very important. Gaussian random processes. They're very useful because of their analytic, their ability to do great things with them analytically. We see that the Gaussian kind of always breaks the rules in a good way, where the Cauchy kind of breaks them in the bad way. Gaussian's good, Cauchy bad. So, let's look at a multidimensional Gaussian random variable and define what we mean by a multidimensional Gaussian random variable. It's something that we've defined previously, but let's remember what it is. If we were to have k dimensions, then this is the density function for the Gaussian random variable, where the k, if you recall, the k, if you recall, was the autocovariance matrix of the Gaussian random variable. Now, this has nothing to do with stochastic process. This is a vector This is a vector of Gaussian processes that are related to each other. And this is a density function for that random vector. If you recall, we visualized this as kind of an elliptical cloud in this k-dimensional space. And the ellipse, the origin of not the origin, but the sense of the ellipse was determined by the covariance matrix. How long and skinny it was, or whether it was circular, is determined by the covariance matrix. Where it was centered in this k-dimensional space is determined by the mean value, m. So the mean value, m, tells where this cloud is centered. Now, the characteristic function for this multidimensional random variable is something we have seen before also. And this is the multidimensional characteristic function of this Gaussian random variable. And it's given by this expression where, again, k is the covariance matrix of the random vector. If we would expand out the characteristic function in longhand, we would obtain the following. I simply here have the characteristic function, and I have the exponent expressed in terms of vector algebra. If we were to expand out that vector algebra into the actual summation process which underlies it, we would get e to the j, and this inner product here of two vectors would be written as a summation. And this term over here is a quadratic corresponding to a double sum, with k sub nm being the nmth element of the covariance matrix. Now, here is something which arises from the characterization of Gaussian random vectors. To this point, we've talked about Gaussian random vectors. Now I'm going to talk about Gaussian random processes. If a Gaussian random process is wide-sense stationary, it is also stationary in the strict sense. Remember, in our derivation that we had last period, we said that this stationarity arrow pointed one direction. It was stationary in the strict sense, it was stationary in the wide sense. For the Gaussian process, it goes the other way too. And only for the Gaussian process that, well, there might be others, but it's the only popular process for which it's true. If it's stationary in the sloppy or the wide sense, it's also stationary in the narrow or the strict sense. So that's pretty neat. Here's the proof. The process is wide-sense stationary, so therefore its expected value of x of t is equal to a constant. And its covariance is equal to just a difference between the two variables. You agree with that? Give me a response. Show me your life. You agree with that? There we go. Okay. You're comatose. So what we're going to do is we're going to choose k points. Remember what we have to do with those k points? We have to show that the density function of those k points is independent with respect to the shift. So we're going to use these two products and the fact that the underlying random variable x is Gaussian in order to show that these k points have a density function which don't shift. We choose k points, and the elements form a k matrix. In other words, we take a stochastic process, which is Gaussian, and if we choose any k values on this Gaussian process, then these k values are going to constitute a k-dimensional random vector. Right? Here's our stochastic process, Gaussian process, and we're going to choose k values here. This is T1, T2, T3, T sub k. We're going to choose these values, and these values then will correspond to a vector. We can concatenate these and express these in a random vector, which is a function of where we take these values. By definition, the process is Gaussian if, no matter where we take these samples, this vector constitutes a vector of Gaussian random variables. Okay? Not only do they have to be Gaussian, but they have to have the same mean and the same variance, since it's stationary. So what we're going to do is we're going to choose these k points, and we're going to form the elements of the covariance matrix. Because in order to characterize this random vector, we have to be able to get our hands around the covariance matrix. The covariance matrix at the nth element is equal to the autocovariance between 2 points at a time. Since the process is wide sense stationary, this is simply a distance, or simply a function of the distance between the 2 points, right? By definition, since it is a wide sense stationary stochastic process. So therefore, the elements of the covariance matrix are given by this covariance, autocovariance matrix, where the argument is simply a function of the distance between the two random variables. So if we have the k points, here's what we have. We have that the characteristic function for the random vector, this is the random vector which was chosen from the samples of the points from the stochastic process. This is a repeat of exactly what we did last time for a general stochastic process, Gaussian process, and not, Gaussian vector. For a general Gaussian vector, now we're going to impose that this Gaussian vector came from samples of a Gaussian process that was wide sense stationary. In that case, what does the expected value of each of those samples become? It simply becomes the mean, correct? So therefore, we can take this expected value outside the summation sign. We have the mean here. In a similar fashion, we've shown the autocovariance matrix is just a function of the difference between the 2 points t sub n and t sub m because of the wide sense stationary assumption. Now, here's what we're going to do. I'm going to shift the points. Remember we said if it's stationary in the strict sense, we should be able to take the points no matter where they are, no matter how many they are, and shift them over by an amount tau. And if the density function at this point is exactly the same as the density function of where you started from, for any value of k, for any value of points, or for any value of shift, then that was stationary in the strict sense. That was our definition of it. So here's what we're going to do. We're going to shift the k points. Before they were just at ti. Now they're going to be at ti plus tau. We're going to shift all of those k points over by an interval of tau. If we do so, well, I don't know if you can see this. I hope you have the notes with you. But let me show you what happens. The autocovariance becomes Tn minus tau and Tm minus tau, and the taus cancel, and you get exactly the same result as you did for the unshifted case. Maybe if we go back here, you can see it a little bit easier. Instead of Tn, we have Tn minus tau. Instead of Tm, we have Tm minus tau. The taus eat each other up, and you get exactly the same expression as you did before. So because these characteristic functions for the shift is exactly the same as for the unshifted, and it's true no matter what value of k you choose, and it doesn't matter where you choose those points, then then we conclude from a wide sense stationary assumption for Gaussian processes, we can assume strict stationarity. We've just proven that. So the arrow from the Gaussian process goes from wide sense to strict sense. For all processes, it goes from strict sense to wide sense. But for the Gaussian, it goes the other way also, which is a really kind of interesting property, because establishing stationarity in the weak sense, or in the wide sense, is much simpler than doing it in the strict sense. Okay, any questions on that? Now I want to talk about a concept known as, it's a brand new concept. We've spent most of the time here today talking about stationarity. Now we're going to be talking about another concept, another type of stochastic process called ergodic. Isn't that a cool word, ergodic? Here's where ergodicity comes from. Suppose that we don't know anything about the mean of a random variable. How can we determine the mean or the expected value of a random variable? Even if we know it's stationary. We know maybe it's stationary, but we don't know the mean. Well, the way that we saw before is we did an ensemble average. We did an ensemble average. And we did this ensemble average by taking a number of realizations of the stochastic process and averaging those processes together. There's a problem, though. In many cases, you do not have the luxury of taking a number of realizations of a stochastic process. You just can't do it. Rather, what you have is one big long stochastic process, and you don't have a bunch of repetitions of it. So the question is can you, not from an ensemble, but from one realization of a single stochastic process, be able to extract the information, such as the mean of the stochastic process, such as the autocorrelation of the stochastic process, from one realization, not from an ensemble. So in many cases, an ensemble of random processes cannot be obtained if parameters of a random process can be found from a single observation, underlying single observation of the process is said to be ergodic. And it depends what you're trying to find. You can have a mean ergodic type of stochastic process, meaning that if you have one realization of that stochastic process, you have the ability to determine the mean of the process, much like you do within an ensemble. You'd estimate the mean by the average of the ensemble. Well, there's a way for a mean ergodic process to determine the mean of that stochastic process from just a single realization. Maybe you want to figure out the probability density function underlying the stochastic process. In such a case, we refer to such processes as distribution ergodic. If you wanted to find the autocorrelation, it would be autocorrelation ergodic. If it was autocorrelation ergodic, you could determine the autocorrelation from one realization of the stochastic process, etc. Let's talk about this heuristically, first of all. Let's talk first of all about mean ergodicity. Here is this is just a bunch of random number generators. This is a result of a random number generator on MATLAB, and the values go from here at the bottom 0 to 1. So this is just a bunch of random variables. If I were to give you this stochastic process, and I weren't telling you that this came from a random number generator, but I told you that this was a stationary stochastic process, do you think you could estimate the mean from it? Yeah, probably, because it's kind of above a half, about as much as it is below a half, and it turns out the mean is probably about here, correct? Just from eyeballing it, you could see that. And if this went along forever, you could determine that mean more and more and more accurately. Does that make sense? So this is a product which intuitively is mean ergodic, that if I gave you one realization of this process, you might be able to determine the mean. How would you do that, by the way? Anybody? Take the sample mean?
Just draw a line down.
Draw a line down.
The sample mean, if you had discrete values.
Okay, what about continuous values? You would integrate. A good estimate of the expected values to integrate from here to here and then divide by this time interval, right? I mean, that'll give you a good estimate. In fact, that's the way we're going to do it. But that doesn't work for all processes. Let me tell you another stochastic process, and I love this one because it's called the battery factory. I run a battery factory, and my battery factory spits out batteries. And what I'm going to do is I'm going to take every battery and I'm going to measure the voltage. Just for pedagogical, educational reasons, assume that this voltage I measure is a random variable that is a function of all time. So whatever voltage it is, assume that it went from minus infinity to infinity, just for purposes of discussion. Is that okay? So I measure this battery, and I get a different battery out and I get a different measurement. I get another battery out, I get a different measurement. The question is, can I look at one of those realizations and compute the average voltage of the batteries off my assembly line? Can I look at one realization? No. That one realization will be just that one battery. It doesn't allow me to go and compute the average of all the batteries. It might be representative in some way, but it certainly would not give me the mean or the average of the batteries coming off of my process. Now, could you, in my battery factory, determine the mean by an ensemble average? Come on, risk it. Yes, yes, you could. You took 1,000 batteries and you did the waveforms and you were to average them, it would just be like taking the average of a number of random variables, right? And you would get the mean eventually. Yeah, so the ensemble average would work. But you could not take a single battery and tell me what that mean was, because you don't have enough information. So my battery factory spits out batteries that do not give me the ability to determine the mean off of one realization. So this is an example of a process which is not mean ergodic. Let me ask you this. Is this say a wide sense stationary stochastic process? Yes, it is. How about my battery factory? Are those values wide sense stationary? Yes, they are. It is a wide sense stationary process. I mean, if you have constants, good grief, the statistics at one interval are going to be the same as at another interval, of course, because it's going to be the constant, it's going to be the same for all values of time. So just because something is stationary does not mean that it is ergodic. So these, I'm attempting to motivate now my discussion for a more precise definition of what we mean by ergodicity, to demonstrate that with stationary processes you can have mean ergodic and you can have not mean ergodic, both of which are stationary. So let's look at mean ergodicity. Mean ergodicity means that we have the ability to determine the mean of the stochastic process, not from an ensemble, but from one realization. And we mentioned how we would do that. What we would do is take something which is referred to as the time average. We would integrate over the stochastic process, say from the interval from minus t to t. If this was a discrete process, it would be a summation. And then we would divide by the interval, 1 over 2t. And in fact, you would kind of expect as t got bigger and bigger and bigger that this would be closer and closer to the average if it were mean ergodic. Do you agree with that? So we're taking the average value. That's the reason this is called the average value. And the average sometimes, at least for ergodic processes, approaches the mean, which is the expected value. So let's suppose that we use this to estimate our mean of our stochastic process. There's two things we would like to know about this. Number one is its expected value. Let's suppose, just for purposes of discussion, that we knew that x of t is stationary. So we know that whatever number we were getting out is just going to be a single number, 7 or something. So it's going to be a wide sense stationary process, so the mean, whatever it is going to be a constant. We don't know what it is. We're trying to determine what it is, but we don't know what it is. What are the two things we would like to do with this? Number one, we would hope that the expected value of x of t would be equal to the mean, right? And second of all, the variance of x of t would be what? Small. Because if the variance of x of t, corresponding to the accuracy to which we know it, is small, then we know that mean within a certain confidence, if you will. So those are the two things we would like. So let's look first of all at x of t and assume that x of t is wide sense stationary. Then the expected value of x of t is equal to, if we take the expectation through the integral here, the only thing we have to integrate on is x, and of course that's equal to a constant, right, under the wide sense stationarity assumption. So that x bar comes out and the integration integrates to 1, and we find out, yes, indeed, we were very intelligent by choosing this because the expected value of the average is equal to the expected value. This is true for all stochastic processes that are wide sense stationary. It's true for the uniform noise that I generated, and it's true for the battery factory. Okay? However, this isn't enough. Because if we estimate this, if we use this as an estimate, we want the expected value to be right on, but we also want the variance of the estimate to be very, very small. So we're good so far. We have the expected value is equal to the mean of the process, the expected value of the time average. This is not an ensemble average, it is a time average. We would also like the variance of x of t as t goes to infinity to approach 0. So the variance of our estimation becomes more and more exact the bigger we make t. This is much like in an ensemble. We would hope that the variance of our ensemble average would go to 0 as the number of elements in the ensemble went to infinity. except this is expressed as a time average as opposed to an ensemble average. If this is true, if the expected value is equal to the mean and the variance of our estimate goes to 0 as t becomes very, very large, we say that x of t is mean ergodic, that we can determine the mean of x of t by looking at a single observation of the stochastic process. So let's go onward. Okay, here's some math. I won't go through the details, but here is a broad sketch. The variance of x of t can be expressed as this. So I'm just taking the expected value squared, the definition of the variance, expanding that out, and then collapsing the two integrals together, and I get this following very interesting result, that the variance of x of t is related to 1 over 4t squared times the integral over a square of the autocovariance as a function of t minus tau. Now, the reason I can use the t minus tau is because I've assumed that the underlying process is wide-sense stationary. In general, it would be t colon tau. It almost sounds like colon pow. T colon tau, except because it's wide-sense stationary, it's t colon t minus tau. So this is just with the math. We're left here, and we're a little bit lost in the math. I mean, as far as determining personality out of this equation, there's not much personality that you can gain. But if we continue, and we're going to continue, and I want you to look at this in detail and ask me any questions about it next time if you have any questions. You'll see this on the homework also. What I want to do is I want to take this minus t to t, and I want to explicitly put it inside here as rectangle functions. I think many of you have seen rectangle functions of this sort before. I use a capital pi. So it's just a window, if you will. So instead of going from minus t to t, I'm going to go from minus infinity to infinity. I'm going to chop it off with window functions here in my integrand. The reason I do this is because it allows me to do a nice variable substitution. I'm going to first of all express my variance in this fashion, which is just a rearrangement of the previous integral. Then I'll make a variable substitution, c is equal to t minus tau. In doing so, I get more stuff. What I get is I get that the variance is equal to, and here's the interesting expression, it's cx of tau times a rectangle convolved with a rectangle. What's a rectangle convolved with a rectangle? It's a triangle, right? And indeed, this is the result that we have, that the variance is equal to the autocovariance times a triangle function d tau normalized by a 1 over 2t here. And this is the actual expression we want, because if this expression as t goes to infinity goes to 0, then we're mean ergodic. If this expression goes to 0, because this is the variance, it's a little off screen here. Can we go ahead and move this over? No, the other way. Okay, good. The variance is equal to this expression. Can we go back the other way? I'm sorry. Okay, this is the definition of the triangle function. And a triangle function is just a rectangle convolved with a rectangle. It's a little pyramid. Okay, so ergodicity. This is what we determined on the last slide if you take out all of the math garbage in between. That the variance of the time average is equal to this expression. If this expression, as t goes to infinity, goes to 0, we have a mean ergodic signal. Thus, a wide-sense stationary random process is mean ergodic if the limit of this, as t goes to infinity, is equal to 0. This doesn't work in the battery factory. There's a similar criteria, by the way, for discrete time stochastic processes where the integral is replaced by a summation. Let's look at the telegraph signal. With the telegraph signal with a randomized origin, we found out that this was the autocorrelation. Do you remember that? Let me ask you intuitively, the random telegraph signal. Remember 1, minus 1, 1, minus 1? We know what the average is, or the mean of that is. What's the mean? 0. Suppose you didn't know the mean and you had an observation of that telegraph signal. Do you think you could estimate the mean is equal to 0 by a time average? One observation. One big long observation. Did I say time ensemble? No. Okay, if you were just looking at one, could you determine it by a single observation? Yeah, it seems that you could. It seems just intuitively that that is a mean ergodic process. Let's see what the math tells us. The math is consistent. If we substitute in this expression in for the autocovariance in the result, you can very easily show with just simple math that this does go to 0 as t goes to infinity. So our intuition is salved. You like that expression? Our intuition is verified. Indeed, this is mean ergodic. Let's look at the battery factory. Now with the battery factory, the autocovariance is not too difficult to show. It's simply equal to the variance of x, where x is the random variable of my batteries that gets spit out from the factory. If I compute this expression for my battery factory, I find out that this expression is always equal to the variance of x and never diminishes as t gets bigger and therefore does not go to 0. So for my battery factory, I do get that this integral does not go to 0, therefore it does not meet that criteria for being mean ergodic. Any questions? I think then we'll probably stop here. That's not mean ergodic. We'll talk very briefly next time about autocorrelation ergodic, and we'll show something interesting. If you have an autocorrelation, don't do that. If you have an autocorrelation ergodic signal, you need fourth order moments of the underlying stochastic process to establish autocorrelation ergodicity. So it gets sloppy really, really quickly. Thank you. You may rustle and leave now.